Welcome to the Intertech webinar on variable speed flow centers. I'm Jeff Hammond with Geo-Flo Products Corporation. We supply Intertech with flow centers, hose kits, and accessories. Let's get started. This webinar will give an overview of the variable speed product offering, as well as why you should sell variable speed, and a case study that shows operating costs and verification of some of the calculations. The pressurized version of a variable speed flow center looks like the panel mount flow center in this slide. You can see the variable speed flow center on the right, and this one has a constant speed pump on the left. If it has only one pump, it's just the variable speed flow center. If it has two pumps, it will use the variable speed pump to try to attain flow. If it can't attain the flow it needs, it brings on the second pump. The Grundfos controller is what tells the variable speed pump and the constant speed pump to speed up or slow down. In this case, we have field wiring underneath this panel. This is where the heat pump wiring connects to the flow center. Everything behind this panel is factory wired. So there's a considerable amount of labor savings since the flow sensor, all the thermistors, and all the controller wiring is done at the factory. It's also a little bit less cost to buy the panel mount compared to all the individual components. And so this is the best way to go for variable speed pressurized systems. This is the field wiring. You can see here there's terminal ACC that comes from the accessory terminal of the heat pump. Y2 is second stage, common, and 24 volts. So these are the only connections needed from the heat pump to the flow center on the low voltage side. And the isolation relays are factory installed. All the wiring between the controller, the relays, the terminals, and the variable speed pump is done at the factory. The non-pressurized variable speed flow center has the exact same pump and the same configuration. It's just simply in a different cabinet. So this is a non-pressurized flow center. Behind the sheet metal is the tank for the non-pressurized operation. We have the pressure and vacuum relief cap on top, so this never lets the flow center tank go into a vacuum, and it never lets it get overpressurized. On the front as well, you can see the flush valves. These are built into the flow center, so you have the capability to purge air from the system by connecting your flush cart. At the bottom we have a drain valve. If we would have to change a pump, you can valve off the bottom and the top and isolate the flow center. So those are all built into the NP series. The variable speed pump right here is just like the pump on the previous picture. This connector is what controls the pump speed. The pump is always powered, and the low voltage connection right here tells the pump to speed up or slow down. Like the pressurized flow center, the variable speed flow center is also available with one or two pumps. If it's a two-pump flow center, the second pump, constant speed pump, goes right here. So it can be field retrofitted into a two-pump flow center if necessary. The variable speed kit for the non-pressurized flow center is like the panel mount pressurized flow center. In other words, all of the components are included in the kit. You can just buy the flow center by itself and buy the individual components, but having a kit gives you everything you need for the installation. All of the ground loop connections, heat pump connections. There's an additional three-way valve that makes flushing and isolating the heat pump easier, as well as a hose kit, all the fittings, a controller, and the controller is on a panel like we saw earlier in the panel mount for the pressurized flow center. So behind this cover are the isolation relays, the field connections, wiring to the controller, to the flow center pump, and so forth. So this makes it much easier from an installation standpoint. Again, the low voltage connections are just like we saw earlier for the non-pressurized flow center, ACC, the accessory terminal, Y2, common, and R. So why would we want to sell a variable speed system? You know, the main thing really is efficiency, but there are also some side benefits. Not only do we get higher efficiency for the system, the heat pump already is very high efficiency, but sometimes having higher pump watts takes away from the system efficiency, even if the heat pump's very efficient. And so we have not only that benefit, but also some startup and service benefits. You'll see in the next slide, there's an on-screen display that shows stage 1 and stage 2 operation. You have entering water temperature, leaving water temperature, temperature difference, and pump watts displayed on the screen. If you go with the flow and temperature version, which has a flow sensor, then you can even see flow rate right on the screen. It'll show in gallons per minute. And if you have that flow sensor, you can read heat of extraction, heat of rejection directly on the screen. So it's very, very easy at startup and for troubleshooting. And in fact, because of the high head of the variable speed pump, in many cases you can replace a 2-pump constant speed flow center with 1 variable speed pump. So there's also a little bit better performance from a pressure drop standpoint. This is the controller that's mounted on that panel for the panel mount pressurized, or in the kit for the non-pressurized. So you can see here the flow rate in GPM. Here's our power, stage 1 or 2, and then temperatures, heat of extraction, and lots of different settings as far as temperature differences, flow rates, and so forth. We typically have a first stage flow rate and a second stage flow rate, or we can use delta T mode, and that one setting takes care of both first and second stage. There is a heating and a cooling delta T setting, so you can change that based on the mode of operation, and it will know which which mode you're in based on the thermistor temperatures. Now, when we look at efficiency, we have, of course, the AHRI numbers that are published on the heat pump, and those AHRI numbers have the pump correction factor built in. The catalog data does not. So if you go strictly to the catalog data in the manufacturer's information on capacity, efficiency, and so forth, it's just the heat pump only. The AHRI data has a pump correction factor, and that's based on the pressure drop of the heat exchanger. So I looked at an example for one of the Intertech units, a 4-ton YT unit, and that heat exchanger pressure drop in the formula above gave me about 83 watts for the pump power correction. So in other words, it takes the heat pump efficiency, the heat pump watts, adds the 83 pumping watts, and then calculates the EER and COP. There are also some other correction factors in there as well, and they're slightly different temperatures than what might be at catalog data. But the main thing is the AHRI data does include pump watts. The catalog data does not. So when we're looking at pump choices, we have to make a selection that's going to give us the best system efficiency. Now, what we're used to are constant speed pumps. There are single speed and 3-speed pumps, but they're just on and off. They can't really change based on demand on the heat pump operation or what the thermostat calls for. So this is 30-year-old pumping technology, very reliable. It's been around for a long time and works well. They're wet rotor circulators. This is an example here of a Grundfos circulator. Here it is on the flow center, and they're not terrible, but they're not nearly as efficient as variable speed. Pardon me, I just skipped a slide. So about 180 watts for the UP2699. Now the larger head pump, the UP26116, it's about 300 watts. So it's actually fairly high usage, energy usage compared to the 2699. If we can use a 2699 instead of a 26116, it's certainly better for system efficiency. So very reliable, been around for a long time, but we do have to be cautious of system efficiencies with the older pumping technology. Okay, so now you can see the curve here. This is a system curve, and in an example, all these others are pump curves. So if we compare, the orange line is 12699, that's the 180 watt pump mentioned earlier. This lighter blue line is the 26116, so it's a little bit higher head. And then we have a green line, which is 2 of the 2699s in series. And finally, this royal blue line is the variable speed Magna Geo. So it's not quite as good as 2 2699s, but pretty close. It's in between the 2 2699s and the 26116. So it's a very high head, very strong pump, and in many cases up to certainly 4 tons, and often with 5-ton units, 1 variable speed pump can actually replace 2 constant speed pumps. So the incremental cost difference between constant speed and variable speed is much more favorable, and you get the energy savings of going with a variable speed pump. Now when we take a look at watts, we'll use those same constant speed pumps to compare again. The 99 I mentioned earlier was about 180 watts. It's typical. It does have a nameplate rating that's higher than that, 245. And the 26116 is about 377 watts on the nameplate, but it's not quite as high as the nameplate rating shows. So you can see here the two power curves as we look at the different flow rates. Let's just pick 15 gallons a minute. You can see it's around 200 watts for this 2699, and the reason I mentioned 180 is because we typically see a one pump 2699 on 3 or 4 tons, so you're going to be in that 9 to 12 gallon per minute range, and that's where that 170, 180 watts comes in. The same pump on the 26116, you can see it's substantially higher watts, way up into 300 plus watts at the same conditions. Even down in these lower ranges, we're still about 100 watts more than a 2699. Now, it's not necessarily a bad thing if you can use one 26116 instead of two 2699s, then you're ahead of the game. But if you just simply replace two 2699s with two 26116s, it's just extra energy use that takes away from system efficiency, even with a very efficient heat pump. Now when we look at the variable speed pump, these are power curves for the variable speed pump. And there are quite a few of them. There are only 12 plotted here just because of simplicity of looking at the various curves. But the pump has a capability of running on 72 different curves from min to max based on what you need at the time. So if the heat pump's running in first stage operation, it needs less flow than if it's running in second stage. So it can simply pick a curve that matches the right pressure drop and flow rate needed, all the way up to the very max curve, which is 230 watts. So when the pump is running full out, like a single speed pump, it's about 230 watts, which is between the usage of the 2699 and the 26116. But anytime you get down into the lower operating ranges, the wattage drops significantly. And this is an ECM motor, so just like the ECM fan motor and the heat pump, it's very, very efficient as you start to dial back the RPMs. And in most cases, on first stage operation, you're going to be down in this 75 to 100 watt range, and possibly even lower depending on the pressure drop of the system. So you're taking a pump that could run at 230 watts max, and 80% of the year when that heat pump is in first stage, it could be way down in this range. So it's easily half of the watts used by a constant speed pump, and in some cases even less than that. Let's take a look at a case study so we can see how variable speed versus constant speed affects the real world. And in this case study, we have a 4-ton Intertech YT unit. It's 2-stage. It has 11 foot of head at 12 gallons a minute with 30 degrees entering water temperature. So I just pulled that right from the catalog. You can see here the heat exchanger pressure drop in foot of head. In this case, we had some fairly long circuits, 800 foot, 3/4 inch circuits, horizontal loop. It had about 20 foot of supply and return piping outside of the building and about 10 foot inside the building, a hose kit on the heat pump, and we're using propylene glycol, in this case 25%. So we keyed the data into the pressure drop software, and we're able to come up with a flow rate and pressure drop so that we could size pumps. This is our end result with all the data keyed in. We had about 40.8 foot of head at 12 gallons per minute. So with that pressure drop and flow rate, we can create a system curve. That's this black line. This tells us what the pressure drop is any place along this line. We know at 12 gallons a minute it's 40.8, but if we only had 10 gallons a minute, you can see it would be a little bit less than 30 foot of head. Where the pump curve, these green and blue lines, cross the system curve is where it actually will run. So if we take a look in this case with a 2-pump flow center, two 2699s, where the pump crosses the curve is right here. So we're at about 12.8 gallons per minute, and we'll use about 376 watts anytime that heat pump is running. Since these are just on-off pumps, it uses these watts whether you're in first stage or second stage operation. And you can see as the stronger head UP26116 crosses the curve, because of the shape of the system curve, there's not a lot of gain really. If you look at where the 26116 crosses the system curve right here, we've gained not quite a full GPM, so about 0.9 GPM in addition with the 26116, but our watts went from 376 all the way up to 572. So in the case of a 4-ton heat pump where we needed 12 gallons per minute, the two 2699s give us more than 12. The 116s were way overshooting, so we're just wasting energy with that pump selection. Now when we look at the same system curve and where it crosses the variable speed pump curve, you can see right here we're at just a little bit less than 12 gallons a minute. In fact, this right here shows the full load, second stage operation. We're at about 11.6 gallons per minute. So we are not quite at nominal flow, but pretty close. This heat pump needs 9 gallons per minute minimum, and 12 gallons per minute would be the nominal or the ideal flow rate. So we're very close to the nominal flow rate, and we're certainly well above the minimum. So on second stage, it is going to run full out. It'll have to run at the 230 watts, which is still quite a bit less than two 2699s, or especially less than two 26116s. It's less than half of those watts. On first stage operation, if we're at nominal flow, the catalog calls for 9 gallons per minute on first stage. We could easily do that, and we're only using 96 watts. So most of the year, 80% of the time, we're going to run at 96 watts. When we need full load, we'll be at 230 watts. Our average is 105. And the pump sizing calculator on the Geo-Flo website does provide the average watts and operating costs so that you can compare the difference between constant speed and variable speed. If you take a look at minimum flow rate, the catalog shows the nominal flow rate and also the minimum flow rate we would want on a ground loop system. We need 9 minimum for second stage or full load, and we need at least 8 minimum for first stage. So if we put in the system parameters for minimum flow rates, now we're only using 96 watts on full load second stage and 74 watts on first stage, averaging about 47 watts if you look at the entire run time. All right, so knowing how the pumps operate and the pump watts, we need to compare to see how that affects our actual COP, which will affect the operating costs. So COP is just simply the coefficient of performance is the output divided by input, and it's BTUs over watts, so we have a factor here to convert it to BTUs over BTUs, and that's this number right here. On this 4-ton system, it has about almost 41,000 BTUs per hour of heating capacity at 30-degree water. It uses a little over 3,000 watts, and its COP 41,000 or so divided by 3,000 is 3.89 COP when you correct it for the difference between conversion between BTUs and watts. So now we can look at a COP at that condition with 26116s, 572 watts or 0.572 kilowatts. Our COP is 3.28, so quite a bit off from our catalog, because the catalog does not include pump watts. This includes the pump selection that we actually used. If we go to the 2699s, now we make that same calculation, and our COP jumps up from 3.28 to 3.46. If we go with the variable speed pump at nominal flow rate, we jump up to 3.62. At minimum flow rate with variable speed, we're all the way up to 3.77 COP. So we increased it half a point from 26116s to our minimum flow with the variable speed. It's a pretty big jump in efficiencies just by changing the pump. We look at part load, same story. The worst part of the situation though on part load is that with a 2-pump flow center, both pumps run whether you're in first stage or second stage. With a variable speed pump, now we can actually determine the flow rate that we need for first stage and only run at the RPMs necessary. So you can see here it's not a great story. Our 26116s on part load take that COP all the way down to 2.93 because of the high wattage and lower capacity. If we use variable speed, you can see we're significantly higher COP, 3.51 to 3.54, depending on whether we use nominal or minimum flow rates. Significant difference. So what it really boils down to, of course, is dollars, and those same numbers plugged in at a 12-cent per kilowatt hour cost. This is sort of an average. It's going to change depending on the area of that you live in, but at least from a comparison standpoint, it's based on 12 cents. You can see if we go with the 26116 pumps, we use about $285 per year just for pumping. We still have the cost, of course, of the heat pump operation. The 2699s, about $100 a year savings. Significant savings with the variable speed if we're looking at nominal flow rates. At minimum flow rates, even more savings. So we probably want to be somewhere in between here. Typically we don't operate at the very, very minimum flow rates, but we could look at what might make the most sense, either nominal or somewhere between nominal and minimum to get the most bang for the buck. And this was assumed on a 4,145 hour runtime for a two-stage unit, running 80% of the time on part load, and also based on the manufacturer's flow rates for those two settings is this one right here, and on the minimum flow rates for this one right here. Now when you compare COPs, in the previous slide we saw the difference between the various pumps. If we compare those then to the AHRI numbers, remember the AHRI numbers do have a pump penalty and also some other conversion factors. In this case, this particular unit had a 4.3 COP, but the temperatures are a little bit different, 32 degrees. It does include 15% methanol. The pump penalty's in there. There's also a fan correction. So we can't compare directly, but we do know from a previous slide, if you remember, that the pump penalty for this AHRI number was 83 watts. So if we go back and look at our various pump selections, this selection right here with this COP was 105 average watts. This selection was 47 average watts. So in fact, if we went somewhere in between minimum flow and nominal flow, we would be right at the AHRI number. And that number is 83 watts. So in fact, if you use variable speed in this particular application, you can tell your customer that your COP is the AHRI COP, which is a pretty good story to tell. On part load 4.9, that's even more important because, in fact, on a constant speed flow center, you'll be operating both pumps whether or not you even need that flow. So really the only way you can get these AHRI efficiencies is with variable speed. With constant speed, you're always using more watts than what is shown in the pump penalty for the AHRI numbers. All right, so let's see how this compares to the real world. These numbers were calculated in the previous slides. In this case, we actually have field data with a 4-ton heat pump, and these are the entering and leaving water temperatures, flow rates, and we came out to 55 watts on this particular job that was being studied, the 800-foot loop circuits and so forth, like the calculations. And on full load, it was using 177 watts. So in our comparison, we had about 230 watts on full load on our calculations, and in reality, in this particular unit, it was only using about 177. So we were very conservative in our calculations, and we still had really, really good results in the real world. In the field test, it was even better than what we calculated. Now those numbers are for single units with a single flow center. On larger systems, we have the same capabilities with a little bit different variable speed technology. This happens to be the Magna III, and it's an insulated cabinet. So this is a sheet metal box with insulation so we don't get condensation at low temperatures. It also has isolation valves that are shipped with it. And then this pump has built-in controls. So for 3, 4, or 5 heat pumps, each heat pump can have a zone valve so that as the heat compressor is running, the water is flowing, and then the pump will adjust accordingly. If only one unit's running, it ramps down the flow center considerably. If all 3 units are running, or all 5 units, however many you have, then it may speed up to match that flow rate. So it is only going to use the flow rate necessary for the number of heat pumps running. And that's a big savings. That allows you to have the same advantages on a larger system that you do on a smaller system. It does have wireless communication. If there are 2 pumps and one pump fails, it will wirelessly signal the other pump to take over. It's capable of operating on a building management system, and it can run in the range of about 30 gallons a minute, about 10 tons, all the way up to way over 100 gallons per minute. In fact, some combinations are closer to 500 or 600 gallons per minute. And certainly Geo-Flo is happy to assist Intertech with any design recommendations or calculations. Thank you very much for attending our webinar. Very much appreciate your time and hope that this information was helpful when considering variable speed flow centers. Thank you.